All right, guys, so we are finally getting on to the derivatives of trigonometric functions, trig functions. So in the last video, we just quickly mentioned that the derivative of sine of x was equal to the cosine of x. And we also said that the derivative of cosine of x was equal to negative sine x. And I just wanted to really quick show you why that is what it is. So if you look at these two graphs, if you look at this first one, if you're familiar with trig at all, you'll recognize that this, hopefully you recognize this is the sine graph, okay? And what I want to look at first is on my sine graph, when I change direction right here, what's happening is my slope becomes 0 for just a minute because I'm going up and then I hurry and change directions. And at that precise moment, I'm not going up or going down. So my slope is going to be 0. And if you look down at the graph below, on this graph, which is showing you the slopes, at those points, I have 0 because my slope is 0. Then the next thing you want to look at is in between these 2 points, my slope is positive. It's going up, 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 and then it reaches this point up here where it stops being positive. And if you look at the slope graph down here, I'm going up, 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 and at this point where it stops going up, it's still positive, but it's decreasing. My slope is decreasing, but it's still a positive number. And if you look really close, and it's kind of hard to see on this graph, but if you look really close at this point, your line is getting steeper, 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 steeper. And at this point, it kind of maxes out its steepness, which gives you your maximum right here. And then your slope is still positive, but it's decreasing. So on my slope function down here, my slope is still positive, but it's decreasing. Now you've got to be really careful because these y values represent your slope, and it's a really difficult concept to wrap your head around sometimes. Even though my function is going down, my slope is still positive. My slope is just decreasing, but it's still in the positive direction. And then I hit the max value, and I'm at 0 right here. From there, my slope is going negative. I have a negative slope, and that's why on this part of the graph, down here, you're in the negative because your slopes are negative because you're going downhill, right? And again, at this point right here, I get a maximum because that's the steepest I'm going to get going down. And then I'm still going down, so my numbers are still negative, but they're getting less negative. They're starting to flatten out, so they're going up closer back to 0. And then again, at this point, it minimizes. That's the lowest it's going to get. So my slope for just a second is 0 for just a moment. And then my slope starts going positive again, which now your slope is back in the positive. So again, if you've spent a little bit of time with trig, you'll start to recognize, well, this just looks like the cosine function. Well, because it is. This is the cosine function. And if we do that same idea again, so when I take all the slopes of my sine function, I get the cosine function. And that's why the derivative of sine is cosine, because that's what shape my slopes make. If I were to do this again, if I took the derivative of cosine and I looked at where does it max out? Well, it maxes out here. Now I'm looking at my cosine shape, and at those points, I'm going to end up with zeros with my super straight graph right here. And then from this 0 to this 0, my slope is negative. So I'm down here, but then it starts going back up. And then from this point to this point, my slope is positive, but then it maxes out and starts going down. And what you get here is the negative sine function. So the derivative of sine is cosine. The derivative of cosine is negative sine of x. All right, so let's do a couple of problems. If y equals 3 sine x over 6, well, the first thing I'm going to do is I'm going to rewrite this 3 over 6 sine of x, because then I just have my constant rule. The derivative of the 3 over 6, this is just a constant, so it's going to stay right there. But I'm looking at my sine of x. My derivative of the sine of x is cosine x. So my y prime is equal to 3 over 6 cosine of x, which just simplifies to cosine of x over 2, because 3 over 6 is a half. And then my second one, y equals 2x plus cosine x. This is just a sum, one of my sum rules for differentials, but this time I am dealing with a trig function, but I do it the same thing. I take the derivative of 2x, so y prime equals 2, and the derivative of cosine is negative sine of x. All right. Now these other trig functions, I'm not going to show you all of them. We're not going to actually go out and create all of these trig functions, but most of them, with what we've already done, you can recreate. So if you really want to see why the derivative of tangent is secant squared, you can rewrite tangent of x. You can rewrite that as sine over cosine, right? And if you do your quotient rule, you're going to end up finding out that your derivative of tangent of x is secant squared of x. Your derivative of cosecant is a negative cosecant cotangent. The derivative of secant is secant tan. The derivative of cotangent is negative cosecant squared. And you're going to need to memorize all these. I've got some flashcards on the way. Hopefully that helps. But one thing I want you to notice is if you take the derivative of a function that starts with c, notice that you always end up with the negatives. So just keep that in mind as you're trying to memorize these, that anything with a c ends up with a negative sign in front of it, okay? So let's put this one on the right-hand side. Sorry, I don't mean to skip over that one. This is just showing you the chain rule. If you have a function inside of your sign, instead of just sine of x, this is saying, what if you had something like sine of x squared or sine of 2x? Then it's telling you that you take the derivative of the outside of the sign and you leave the inside the same. And then you multiply by the derivative of the inside. Okay, so this is just like the chain rule. You derive the outside, keep the inside the same, and multiply by the derivative of the inside. And we're going to practice those here right here. Let's just get through some examples today. We'll do some more in class and answer questions if you still have any. So this first one, y equals 2x plus tan x, that's just our sum rule. So my y prime equals the derivative of 2x, which is just 2, and the derivative of tangent of x, which, until you have them memorized, we'll keep that right there. The derivative of the tangent of x is the secant squared of x. So that would be your derivative. That would be your y prime. Okay, now dropping down to the next example, we have got 3 minus cosine of x over sine of x. Now, you can use the quotient rule. That's one way to do this problem. But you can also, with trig, it kind of opens up some new doors for you to kind of move things around. Another way, and I'll show you since we're talking about trig functions this time, but if I take this 3 minus cosine x over sine x, I'm going to split that up into 3 over sine of x minus the cosine of x over sine of x. So I'm just rewriting, this is still y equals. Well, 1 over the sine of x is just cosecant. So I can rewrite that 3 cosecant of x by moving that up. And then cosine of x minus sine of, or divided by sine of x, well, that's just cotangent of x. So now instead of the quotient rule, I've just got a difference rule. So I start to find y prime. I find the derivative of this first part. So I've got my constant out in front. My cosecant x, the derivative of cosecant is right here, negative cosecant of x, cotangent of x. So there's the derivative of the first part. Now I've got to take the derivative of cotangent of x. So if I go up here, the derivative of cotangent is negative cosecant squared. So that's negative cosecant squared of x. And I don't have anything else inside my function, so x works just great. So now if I simplify, we've got y prime, and we'll just clean this up a little bit. Let's move that negative out front. So -3 cosecant x cotangent x. And then these two negatives become a positive, and I get cosecant squared of x. Okay, and that looks like a great answer. It looks really messy, but that looks like a great answer to me. You could rewrite this with sines and cosines if you wanted to, but I'm okay with this form, and I wouldn't worry about simplifying it beyond that if I were you either. All right, so our new function, y equals -3x secant x. So this is just a product rule. So remember, product rule, we take f prime of g and we add g prime of f. And I know that's the shorthand. Hopefully you can translate what we're saying there. So f prime, so here's my f function right here. This is my g function. So f prime is just going to be -3. G is going to be my secant, well, skipping letters, secant x. So -3 secant x, and then I have to plus g prime. So here's g. Now I've got to take the prime, the derivative of secant. So if I look right here, the derivative of secant is secant x tan x. So secant x tan x, but be careful, because remember I have to take g prime f, or the derivative of the second times the first. So I need to multiply that by -3x. So when I rewrite that, -3 secant x plus, oh, let's not write plus because we're going to move that -3 to the front, -3x secant x tangent x. That's a great answer. So is this one. If it didn't match the multiple choices, you might consider factoring out that -3, right? We can pull out a -3 and a secant. So I can pull out -3 secant, and I'm left with x minus, oh, nope, that one didn't have the x. It's my next one that has an x. All I've got is a 1. 1 minus this 3 factored out. The x did not. The secant factored out, but the tangent stayed inside. There we go. So if it doesn't match the multiple choice, simplify it a little bit and see if you can find an equivalent answer there, okay? Now what happens when we use those chain rule formulas? So instead of just sine of x, we have things like tangent of 4x. So just like the chain rule before, my y prime, I'm just going to take the derivative of the outside of just the tangent part. And remember, derivative of tangent is secant squared of 4x. So that's just the derivative of the tangent part. But then I've got to multiply by the derivative of the inside, which is 4. So I'm going to multiply by the derivative of the inside. So when I rewrite that, y prime equals, let's move that to the front, 4 secant squared of 4x would be your final answer for that one. Okay. How about this? Root sine of x plus 2. Can't really do much deriving when I have a square root. So let's rewrite this first as sine of x plus 2, but let's raise that to the 1/2. Remember that root can go up top as an exponent. So now if I take the derivative, I've got to take the derivative of the outside, which brings the 1/2 in front. I leave the inside the same, sine of x plus 2. And then I have to minus 1 from my exponent. So 1/2 minus 1 becomes -1/2. And I'm not done, because I need to remember to multiply, chain rule, multiply by the derivative of the inside. Well, the derivative of 2 is just 0, but the derivative of sine x is cosine x. So when I rewrite this, I can rewrite it if I want to. This is a great answer, but again, free response, we would accept that. Multiple choice, they might simplify it a little bit further. This -1/2, I can move to the bottom. So I can put that sine x plus 2 on the bottom, and that 1/2 can change back to a square root. So I just moved this whole thing. I just moved it to the bottom. All right. And then my 1/2, my 1 can stay on top. My 2 can go to the bottom. And I have a cosine x on top. So you probably don't need to write that 1 because we do have a cosine x left over on the top. So I get cosine x over 2 root sine x plus 2. Both of those are acceptable answers. Now, f of x equals sine cubed of 2t. Now, we usually put this cube right here so you don't mix it up. Just remember that the sine of 2t cubed inside parentheses is different than the sine of 2t all raised to the third power. And this is what we have going on. That 3, what this is saying is that the entire thing is being cubed. So when I rewrite that, just so it makes my power rule a little bit easier, I'm going to change this f of x equals the sine of 2t, and I'm going to put parentheses and put my cubed up here. Just so that I guess I should make this f of t, huh? Why are we using f of x when our variable is a t? I want to make sure that that 3 is on the outside. So when I use the power rule combined with the chain rule, combined with the trig rule, combined with the constant rule, this 3 comes down. So I get 3 multiplied by the sine of 2t. The inside doesn't change, and this becomes squared. And then what else? We need to multiply by the derivative of the inside, right? So the derivative of sine is cosine, and I leave the inside the same. But because the inside is 2t, there's also a chain rule going on right there. When I take the derivative of this part, I have a chain rule in there. So the derivative isn't just cosine 2t, it's cosine 2t multiplied by 2, because I have to take the derivative of the inside of my sine. So there's a lot to keep up with on what looks like a pretty basic problem. So if I want to rewrite this, I can say 3 sine, and I'm going to put the squared back right here, 3 sine of 2t squared multiplied by, I'm going to move that 2 out front, 2 cosine of 2t. And then to simplify even more, let's get that 2 and the 3 in front together. So sine squared of 2t, 2t multiplied by cosine of 2t. So all of these are acceptable answers right there. All of those work. It just depends on what it's asking for on a multiple choice. On free response, stick with that top one. And I know I keep saying that over and over and over as we're doing these problems. But it's kind of a big one. It's something to keep in mind so you don't lose points for making algebraic mistakes, okay? All right, last example, at least until you come to class. Find the equations of the tangent line and the normal line. You're going to see these examples a lot. It's one of those that it's a popular AP concept, so we want to make sure that we practice this a lot. We want to find the normal line and the tangent line at this point. So it gives us the point and it gives us the function. So the first thing I'm going to do, I already have my point. I don't have to find my x and my y. Here's my x, here's my y. But I do need to find the slope. Remember, to do the tangent line, I need a point and I need a slope at that point. I've got the point. Now we need to find the slope. So I'm going to take the derivative of x over sine of 3x. And I really don't want to leave it in this form. In fact, let's rewrite f of x. Let's write this as x multiplied by the sine of 3x raised to the -1. Because what that does is the inverse, this is saying the sine inverse, that just becomes x times what, the cosecant of 3x. And I can get rid of that exponent completely. So now I just have a product rule, x times the cosecant of 3x. Well, I have a product rule with a trig function with a chain rule because there's a 3x on the inside. So a lot to keep track of here, f prime of x. Product rule first. So I need f prime. So my first function, the derivative of x is just 1, and I leave my second function the same, cosecant of 3x. And then I need to add the derivative of my cosecant, the derivative of my second function. So let's find the derivative of this part right here. And here's where we've got to be careful that we don't forget about that chain rule. First of all, the derivative of cosecant is, what was it? I think it's cosecant cotangent, right? So cosecant, and let's double check. We're all remembering these. Cosecant is negative cosecant cotangent. Okay, so we're going to do negative cosecant of 3x times the cotangent of 3x. And that's just the derivative of the outside. Now remember, you have to multiply by the derivative of the inside. So don't forget to multiply by that 3. And don't forget that, remember, we're doing f prime times g plus g prime times f. Well, here's my f prime. Here's my g. This entire thing is my g prime. I can't forget to multiply by f, which is just x. And that's the one that's going to get forgotten the most. We're going to forget that all the time because we're going to get hung up doing the derivative of g, and we're going to forget that f that goes at the end, that other part of our product rule. So when I rewrite this, we can drop the 1. So f prime of x is going to equal the cosecant of 3x. And this becomes, I'm going to move this 3x to the front, minus 3x cosecant 3x cotangent 3x. All right, I'm feeling okay about that one. Now we want to plug in, because this is our slope formula. This is our derivative. But I need to know the slope when x equals pi halves. So we're going to take f prime of pi halves. When is x? What happens at pi halves? So I take the cosecant. Pi halves, this becomes 3 pi halves minus 3 pi halves. Cosecant 3 times x is 3 pi halves. Cotangent of 3 pi halves. Which hopefully you're hearing some reminders about the unit circle, right? You keep hearing, oh, 3 pi halves, 3 pi halves. So if I think about my unit circle, well, actually, let's write this over here so that we have a little bit of space. If I'm looking at my unit circle, so now we're going to consider that big poster up there on the wall that you've memorized, right? If I think about my unit circle and I think about the point 3 pi halves, because what this is asking is at this point, at this radians, at 3 pi half radians, what's going on with the cosecant, and cotangent? Well, at 3 pi halves, my ordered pair is 0, -1. That's my ordered pair on the graph. And remember that the first, that's my cosine, and this is my sine value. So when I look at this problem, here's what I see. Cosecant is the inverse of sine, right? I should be careful how I write that. The cosecant is sine just flipped over. So if my sine value is -1, if I flip that over, I still get (1/1). I still get -1. So the cosecant of 3 pi halves is just -1. And then I'm going to minus 3 pi halves. And then I've got cosecant again of 3 pi halves. So that's multiplied by -1. And then I need to take the cotangent at 3 pi halves. Well, cotangent is just cosine over sine. And my cosine is 0. My sine is -1. So my cotangent is just 0, which is great because it means this 0 multiplies by this, and all I'm left with is my slope of -1. So f prime at pi halves, my slope is -1. So now I can go ahead and plug everything into my y minus y1 equals m times x minus x1 formula. So I get y minus a -1 equals my, oh, not -1, sorry. That's my y1. Where's our y1? Up here at the top, right? my y value is negative pi halves. So y minus negative pi halves equals my slope, -1, multiplied by x minus my x1, which was just pi halves. That's a great answer. Free response, that looks great. If you wanted to simplify, you could say y plus pi halves equals negative x plus pi halves, which I think is kind of a cool concept here, because when I move this pi halves over, I end up with y equals negative x. And I'll show you what that looks like on the graph here in just a minute. So this is going to be my line, but this is also my line, and I would take either of those answers. Okay, so this is my tangent line formula at that point. Now my normal line, remember I take my slope at that point, and I need to take the opposite reciprocal. So the opposite of -1, excuse me, is 1. And when I flip that over, it becomes 1 over 1, which is just 1. So the only thing that changes in this formula for my normal line is y minus negative pi halves equals, instead of a -1, I get 1, x minus pi halves. My slope, instead of being -1, just changes to +1. And then you're welcome to simplify that beyond, but for me, that's a great answer. What I want you to look at is, I want to look at this function. I want you to see what it looks like, because it's kind of a cool one. So we've got x divided by sine of 3x, right? Did I put that in there? X divided by sine of 3x. Okay, so when I graph this function, I get a pretty cool picture. I'm getting closer and closer to 0, and then I start going away again. And I think that's a pretty cool image, but this is the best part. If I look for my tangent line, remember I can do second draw, and if I want to draw my tangent line, I hit 5, and I plug in my x value, which is pi over 2. And when I hit enter, look at my tangent line. It hits all of those. And I think that's a pretty cool image right there, that it just barely, if you zoom in, it's tangent to all of those different curves right there. And if you look down here, it says that your tangent line equation is -1.000000x plus 7.06 e to the -6, so 0.000007. Which is basically y equals -1 x. Those two become insignificant there, which is what we got. We said that our tangent line, if we simplified it, was y equals -x. All right, bring your questions to class. We'll do some more examples and have a little bit more fun with these trig functions.